Everything is on just one unit plan this time, the storms, floods, and tornadoes unit plan. And we're just going to go through each of the reasoning targets one by one. So, okay. Reasoning target. I can read and interpret weather maps and other meteorological data and utilize them to make short-term weather predictions. There is a lot involved here, so we're just going to go over some of the things that we've talked about, starting with the station maps. So specifically, this is a station map or station model, and and I'm not going to give you one that has any more sort of stuff than this. They do get a little busier than this, depending on where you go to look. But let's just go around the circle here, starting with the amount of cloud cover. That's what the circle is showing you. So for this example, it's about 75% cloudy. I guess I skipped this one, is the pressure. We haven't really ever used the pressure, but that's what that number is. The wind direction is indicated by this line. The direction is, the wind is basically blowing towards the circle as if this was an arrow, and these are the feathers at the end of the arrow. The longer the little feathers and the more of them, the faster it is. Right, so in this example, the wind is blowing from the southwest at 15 knots. The number on the bottom here is the dew point temperature, so that's the temperature at which condensation will occur. And the number up here is the actual temperature. So the closer together these two numbers are, the more saturated the air parcel. All right, we have a little weather symbol. Sometimes that's missing, but it can mean any of these things from rain to snow, drizzle, etc. Anytime there's some sort of precipitation, you might have a symbol to represent that. The fronts we're going to go over again, but just as a refresher, cold fronts have triangles. The triangles are pointing in the direction that the front is moving, so it will be cold behind them and warmer in front of them as the cold moves to overtake the warm. Warm is shown with half circles. Stationary is shown with every other. And occluded is when they're all on the same side, one than the other, triangles, then circles, half circles. And we'll look at these again in a second when we talk about sketching fronts. Okay, so with our station models, we ought to be able to look at a map that has station models on it and say a few things. We ought to be able to figure out where it's hottest, where it's coldest, where it's windiest, what direction the wind is going from, how cloudy it is, where we have precipitation. So here's a bunch of precipitation symbols or snow, all of these things. Another view that you might see of a map would be with the high and low pressure symbols, right? So this one has high and low pressures and it has fronts on it, okay? So here's a great example of a warm front. That means we would expect, it actually doesn't look like the best of examples, but we would expect that it's warmer on this side and colder on this side. Sometimes the maps are too zoomed out for that sort of detail to show up, but let's see. This is a really good example of a cold front, right? Because you have temperatures in the 50s on the cold side and then much warmer temperatures on the other one. And that's what we would expect, right? So anytime you're asked, you know, is this what we would expect? That's something that you could check to make sure that the cold and the warm are on the proper sides in relation to where the front is and the direction that it's moving. So the direction, oh, my pen's not working. Oh, it's the wrong pen. The direction would be in towards the side that has the symbols. Let's see. We might expect this cold front to catch up with this warm front because cold fronts are faster. We might expect a high pressure area to be clear and sunny, like it is over here. That's what we expect for high pressures, and at low pressures, we expect it to be rainy, like it is over here. Again, you'll often find things that don't quite follow this pattern because of local specifics. But these are the things that we would expect. We expect low pressures because that's where we have rising air. We expect that to generate cloudy and rainy conditions, and high pressures we expect to be a bit more clear. So if you were to examine a map, you ought to be able to figure out where to expect rain, where to expect clear skies, and how the weather is going to change in the near future based on the location and the movement of different fronts. Another type of data that you might be asked to examine would be a graph like this. So this has temperature on the x-axis and pressure on the y-axis. Now the pressure is greatest at the surface, and then it gets less and less and less as you go up through the atmosphere. So this is really an elevation axis as well. It can be thought of as the same way. Things to look for here, anytime I ask you to look at these, we're usually trying to figure out if it's going to be stormy or not. So what do you need for storms? Well, you need warm air, warm wet air in the lower troposphere. So this part of the graph is telling us that the atmospheric parcel is warm. This second line over here is actually referring to the dew point temperature. So that's the temperature at which condensation would happen. And anytime these two lines are close together, that means that the air is really saturated with water. It's close to being saturated with water. It has a lot of water. So when these two lines on the bottom are close together and they're still sort of warm, then you have warm wet air. This is a temperature inversion, which I'll talk more about in a second, but that's that warm capping layer that's gonna not enable this lower air to rise. And at that temperature inversion, the fact that the dew point temperature is dropping so much tells me that that is a dry atmosphere, and then it's colder in the upper atmosphere. So this is an example of a plot that would indicate probably storms are possible, tornadoes are possible. Other things to look for, other data sets that we could examine would be to look at the upper atmosphere. So this is, so if you were down at sea level, pressure would be closer to 1,000. So we're up a little bit, up where we would sort of expect that temperature inversion to be. And up here, the number one thing that we look for are ridges and troughs, okay? So there we have a ridge, a trough and a ridge. So the trough is where you see all of the downs, and wind in the upper atmosphere tends to blow along these lines from west to east, okay? So what's happening here is that cold air is coming down into the states, and so we would expect along the trough line for it to be cold. Over here on the ridge, on the ridge axis, we'd expect it to be warm because in this case, the wind is blowing upwards from lower elevations, and at lower elevations, it's typically warmer because you're just closer to the equator. And so that's creating warm air along the ridge. This relates to the weather because it's going to actually create low pressure zones, which are going to be associated with bad weather conditions. And because it's all blowing towards the east, then you're actually going to have your number one place for storms to be just to the right of that trough, okay? So if you were asked to make a weather prediction based on upper atmosphere ridges and troughs, you would expect there to be cold temperatures here, warm temperatures here. You would expect there to be storms just off from the cold zone, and you would expect sunny skies just east of the warm zone. Okay, another thing that we talk about is air masses and all the different types of air masses, right? So basically you have to figure out the latitude that the air mass came from and whether it originated on a continent or in the oceans. So this is how we name them. So you've got your maritime tropical, meaning it formed at low latitudes where it's warm and it formed over the ocean. You've got your continental tropical, which is like this one here, forming on the continent but still at fairly low latitudes where it's warm. And then you've got your polars and your Arctic, again continental or maritime, just depending on if it formed over the land or over the ocean. The other thing about that, of course, is if it forms on land, that air mass is going to be relatively dry. And if it forms out over the ocean, the air mass is going to be have a lot of moisture in it, and it'll be fairly wet. So let's see. I realize I am onto a different reasoning target than at first, right? So we've covered all of the data, and now we're starting to describe physical processes. Did anyone have any questions about interpreting weather maps and other meteorological data before we keep going on with the physical processes? Okay, in that case, we'll go on to our next reasoning target. I can describe the physical processes that result in the complex movements of air masses, including the generation of thunderstorms and tornadoes. So we've already covered the air masses. Next, we need to talk about high and low pressure zones. So high pressure would mean air is descending So we have falling air, and I'm drawing a side view right now. Everyone should be able to draw both side views and top views of high and low pressure systems at this point. So this is a high pressure system because all the air is pushing down onto it. Once it reaches the surface, that air has nowhere to go except outwards. And if you were to look in the upper atmosphere, it would be coming in like this. If we did a top view, then we need to remember that the Coriolis effect is going to impact this. So from top view, if I look at the center, then I know that the winds need to be moving away from the center. And due to the Coriolis effect, I know they're going to be curving to the right. So I'm going to draw my up arrow first because it's easiest. And then I can just draw all of these. So that's a top view of a high pressure zone. Now let's just do the same thing for a low pressure zone. This is the ground. We'll put our low pressure zone there. Low pressure means rising air. So it's going to rise, and it will actually diverge aloft. That just means that they move apart. And in order for that air to rise, it has to come somewhere. It's going to come in like this. It's a little messy, and I'll just draw another nicer one. So that's my low pressure. Now this time, that means that when I draw my top view, all of the wind needs to be moving towards the low pressure system. I'm going to again start with my up arrow just to make sure I don't make any mistakes. And looks like this in top view. Again, you have to have that spin due to the Coriolis effect. Then we talked about all the different ways you can create thunderstorms. There's 4, with the first one being frontal, but we're actually going to take this opportunity to talk about all the different fronts, even though only the cold front is really associated with thunderstorms. The other ones still bring bad weather, so we'll just go ahead and talk about all of them. First, we need to be able to draw side views of all of them. So this is the ground, and this is my cold air. My front would be here, where the cold and the warm meet. A cold front, so that means the cold is advancing on the warm. When it does, it rapidly forces that warm air upward, which is going to lead to storms. The more rapidly that the air is forced to rise and the higher it gets, the more severe the storm system. A warm front, the ground, this time I'm going to put warm, no. Warm front, this is still the front, in this case moving that way. But the warm air is still being forced up over the cold, and this can lead to gray skies and clouds. It can also lead to storms, it's just not as common as the cold fronts. The occluded front, here's the ground. This is the one that's been cut off. So here's the side view. So the warm air is being forced upwards because a cold front has overtaken a warm front. So it would have looked like warm front, cold front, but the cold front is moving faster. So once they occlude, the symbol becomes this because those the cold front overtakes the warm front. So again, that just, I've just gone to the top view over here. This is cold, warm, cold, and now it's cold, cold. Hot air has been forced out of that system. So that's what's going on with an occluded front, and it can bring bad weather, rain, storms, etc. The final type of front is the stationary front, and in a stationary front, I could draw either a warm front or a cold front. It doesn't really matter. The difference is that there's no motion this time. The air isn't moving at all. The symbol there is this one. So there's just no relative motion between the cold air and the warm air in this case. Okay, so those are all of our fronts. They all lead to bad weather. The stationary front can lead to just days of gray drizzle. The warm front can lead to gray days and drizzle. The occluded and the cold front are more likely to maybe have some storms, with the cold front being most associated with thunderstorms. Okay, but that's only one way that we can make a thunderstorm. Another way is convective. This is what we call it when we have the sun warming up the earth all day, and that makes warm air, and eventually that warm air is going to be warmer than its surroundings, and so it rises. Okay, and as it rises, it's going to cool adiabatically. Eventually, the saturation point will be met, and we expect to form clouds. Those are supposed to be my clouds, and have thunderstorms that way. Another option is the low pressure system or convergence. This is going to look similar to the convective case, except in this time, you really need to make sure that you draw the air moving towards that low pressure zone and diverging aloft. It'll still make the mechanism for making clouds is the same in every case. As air rises, it expands. This forces it to cool adiabatically. As it gets lower and lower temperatures, the relative humidity changes, becomes closer and closer to 100%. Once you're at 100%, that means that the air parcel is saturated, and at saturation, that's when the temperature of the air parcel is equal to the dew point temperature of the parcel, and condensation occurs, and you can have your clouds. The next step, since I'm already saying it all, the next step then, so when condensation occurs, that actually you have to remove energy from the water vapor. That energy is dumped into the atmospheric parcel, the parcel of air, and that energy helps it to stay warm and to continue rising. But at that point, the rise will be due to the rate of cooling will change, and it will follow the wet adiabatic lapse rate instead of the dry adiabatic lapse rate. Nor we're going to talk about that again when we look at an atmospheric parcel go through that transition. Orographic. So this is just a really fancy word for mountain. So here's my hill or mountain. And if wind is, well, in the US, it typically blows from west to east. If the wind is forced up, it likely will reach some altitude where it is saturated, and you'll have clouds and rain. So 4 different ways to create thunderstorms. Frontal, primarily meaning cold fronts. Convective, meaning the ground is heated by the sun all day, creating warm air that rises. Low pressure, also rising air. And orographic, which forces the air up over a mountain. All right, so putting some numbers on it now and getting back to these ideas of instability and lift. Slightly different ideas. So instability refers to the atmospheric parcel remaining warmer than its surroundings, and so it will continue to rise. Lift is anything that gets it to rise in the first place. So that's often associated with divergence aloft, which again is just this part of the low pressure system, what's happening up high. It's diverging, and that's going to suck the air up from the bottom, which is going to suck it in from the sides. Okay, so that's what the lift is referring to. And the instability is about keeping the air parcel that you're thinking about warmer than the surrounding environment. So if we want to know if a parcel is stable or unstable, stable meaning it's not going to rise upward, and unstable meaning it's warmer than its surrounding, it's going to rise, and then we are going to start with the initial temperature of that air parcel, and we're going to let it cool at the appropriate rate and just see what happens. So in this instance, the dry adiabatic rate is the only one that we're going to model, and it looks like that is 5.5 degrees Fahrenheit per 1,000 feet. So all I need to do is 112 minus 5.5, which equals what, 106.5? You can yell at me if I get that wrong. And then we would write 106.5 here. And then as we go up another 1,000 feet, we would do the same thing. 106.5 minus 5.5 give us 101. And as long as this temperature in this bubbles is higher than the temperature over here, as long as this is higher than that, then the air parcel will rise, okay? But if you ever get to an altitude where the number in the bubble that you're examining is less than the outside temperature, at that point it would stop rising and you wouldn't have lift anymore. which brings us to our mountain examples. We did a few of these in class, and there is one on the assessment. So we'll go ahead and do this one together. Things to look at, we have a starting temperature. We have a dew point, okay? As soon as the temperature that we're considering reaches the dew point, that means the air is saturated and we have to switch to the saturated adiabatic lapse rate. Until then, we use the dry rate. So to start with, we're going to use the dry adiabatic lapse rate of 5.5 degrees. So 94 point, oh, I should have got a calculator. That's okay, we can do this. 94.5 minus, oops, minus 5.5 is going to be 89.5, but we're rising by 2,000 feet, not 1,000 feet. So I am actually going to use a dry rate of 11 degrees per 2,000 feet, right? Because instead of moving up 1,000 feet, I'm moving up 2,000 feet, so that's going to be 11 degrees each time. So that makes this 83.5. All right, I'm still higher than my dew point. Okay, so subtract another 11, 72.5, 61.5, 50.5. Okay, this is the dew point temperature. That means that we expect condensation. This is when we expect our clouds to form. It also means that this atmospheric particle is saturated, and so now we have to switch to the saturated adiabatic lapse rate of 3.3 for this final temperature rise. Rise of the atmosphere, partial lowering of the temperature. So 50.5 minus 3.3 is 47.2 degrees. Okay, so now we've made it all the way to the top of the mountain. We know when the air first became saturated, which is the same thing as when clouds condense. And it's the same thing as 100% relative humidity, and it's the same thing as when the temperature became the dew point temperature. Those are all just synonyms. Now we want to figure out how hot it's going to be down here on the other side of the mountain. And so we're going to heat up this atmospheric parcel. Now, as soon as we raise its temperature even a tiny bit, it won't be saturated anymore, okay? And so when we go down this side, we need to use the dry rate, okay? So the dry rate was 11 degrees per 2,000 feet. You know what, I'm going to go back and look at the 5.5 per 1,000. So it's 5.5 per 1,000 feet times 12,000 feet. That means that the temperature down here equals 5.5 times 12. Or, let's see, 6 times 1, is that 66? That doesn't seem right. 12,000 times 5.5, or, okay. Is that right? If you have a calculator, you can go ahead and check me. Does anyone have any questions about how I solved this problem or any of the previous problems?
Can you go over how you found the second sea level again?
This one?
Hello? Yeah, the second sea level.
So going down the other side of the mountain. Oh, you know what? I did it wrong. So going down this side of the mountain, and I'll replace this with the right number, you need to figure out the change So this is equal to 66 degrees change. So the change in temperature as you do this drop, so I went back to my dry adiabatic lapse rate. I went back to my dry adiabatic lapse rate, and I looked at how many thousands of feet I have to change. So this is 5.5 feet per 1,000 feet. Oh, 5.5 degrees per 1,000 feet. And we have to drop by 12,000 feet. That is a temperature change of 66 degrees. And it's going to be increasing during that time. Falling air increases in temperature because it's getting smushed and compacted. And so there's a temperature change of 66 degrees, but we already started at a temperature of 47.2. So the temperature at sea level is actually going to be 47 plus 66, which equals wait, 47.2 plus 66 equals 2. 300. Oh, sorry, my PowerPoint is not letting me do this. 2.6 plus 3 plus anyone know what it is? Nope. Nope, no one commented mistake. Okay.
Shouldn't the 12,000 feet be 43.9 because wouldn't you take the saturated rate doubled?
So yeah, but you want to use the dry rate. As soon as
Well, I'm talking about because when you hit the dew point, you switch to the saturated rate. Wouldn't you double that just like you did the dry rate?
Oh, yes, that is something I did incorrectly here.
Okay.
Yes, you are correct. So what should the temperature at the top be?
I got 43.9.
I'm gonna erase some of this. This is getting crazy. Okay. Okay, page 2. 43.9. So you're right, when we switch to the saturated rate, we're still going up by 2,000 feet. So we definitely needed to double that. So that should be 50.5 minus 6.6 equals 43.9. Now, on the way back, we're going to use the dry rate. And so we can either do 5.5 degrees. Yeah, we'll just write that one down. 5.5 degrees per 1,000 feet times 12,000 feet, which does still, as someone verified, that equals 66. I believe so. So that's our temperature change, but we start at 43.9. We add 66. This time we get a little better. Seem right? It is a very hot eastern side of the mountain. But that is how you do the problem. So I'm just going to reiterate, sorry about for that miscalculation. So when you start on the left side, make sure that you're using the right rate for the right change in elevation. And then just keep letting that air cool down until you figure out where saturation occurs. Switch to the dry rate, double check you're using it properly, make it up to the top of the mountain. Switch to the saturated rate, double check you're using it properly, move up to the top of the mountain. At that point, when you go back down, switch back to the dry rate, make sure you're using it properly, and then add that temperature change to the air that you started with at the top of the mountain. Okay, hopefully I didn't confuse you more than you started. More questions about this one or anything I'm missing? Okay. Okay, so we are going to go on, but we could come back. I might actually make a separate video just for this question where I do it properly from start to finish. There's a chance I might even cut this out of the version that I post online, just so I don't confuse people. Okay, that is the most mathematically complicated thing that you will be asked to do. So getting back to understanding the fundamental processes. Again, the reasoning target we're thinking about is I can describe the physical processes that result in the complex movements of air masses, including the generation of thunderstorms and tornadoes. Must know the recipe for a tornado and why Tornado Alley is so prone to those. So this image that I have here is showing sort of the normal conditions that exist on Earth. So the sun heats up the ground, which heats up the atmosphere. So that's why it's warmer near the ground and it gets cooler as you go up. And as air rises, it cools due to adiabatic expansion because there's less pressure on it, and so it's expanding and it has a larger amount of space for the same amount of energy, and that forces the temperature to drop. If you really want tornadoes, if you really, really want them, there's a few things that you need. You need warm, wet air in the lower atmosphere. You need that for any storm. You need something to provide lift. So that could be a front, it could be a convective system, it could be a low pressure zone, whatever it is. You need really cold air aloft, right? So the bigger the pressure, the temperature difference between the warm air on the bottom and the cold air on top, the faster that warm, wet air is going to rise, which is going to let it get just higher and higher up into the atmosphere. So that's sort of getting into this idea of instability, right? So that again, the instability was when your air remains warmer than the surroundings, so it can continue to rise and get really high. So the final thing, if you really want to generate tornadoes, is that inversion layer, okay? So this graph is a bit misleading because this cooler air on the bottom, it is actually fairly warm. So the sun is still heating the ground, which is heating the atmosphere. However, there's this inverted layer that's even warmer. So the air that is warm here and it's rising up, it can't make it pass through the inversion to this cold air, and it's forced to stay down here. And while it's down there, it can continue to heat up, right? So the sun is still just passing through all of this, the warmth of the sun, the energy of the sun, and heating up the ground, which is heating up the atmosphere. This lets the air on the bottom, which if it's warm and wet, it gets warmer and warmer and warmer, meaning the temperature difference between the lower atmospheric air and the upper atmospheric air is getting larger and larger, so that once this inversion finally goes away, this air is going to skyrocket upward. And you should also be able to see that in these types of graphs where you have warm, wet air in the lower atmosphere, a temperature inversion of dry air, and cold air up high. Those are the things that you look for to see if you might be expecting tornadoes. Tornado Alley in the US is specifically quite prone to these because it has this perfect blend of conditions. So you've got warm, moist air. So this is a maritime tropical air mass coming from the Gulf of Mexico here. You've got warm, dry air from Mexico. So that is a continental tropical. The warm, moist air comes in on the bottom. The warm, dry air comes in the middle, and then cold, dry air, so continental polar, usually could be continental Arctic, but I think it's usually continental polar, comes in from the north, from Canada, and all of these three air masses converge in Tornado Alley. So that gives you your warm, wet air, your dry, warm air capping layer, and your cold air aloft. The three things that we said that you needed, 1, 2, 3, to create a perfect scenario for storms. Okay, we are going to move on from the physical reasoning behind these things to talk about mitigation. So tornado damage, we talked about the enhanced Fujita scale, and we spent a lot of time trying to categorize damage. You will have to do that at least once in these assessments. So you'll be given an image like this and asked to rate that damage, and you really just need to be sort of within 1. So take a second and just think to yourself what you think this is on the scale. So I think this is most likely a 3. If you said 2 or 3, that's pretty good. 4 is also okay. But 3 would probably be the best answer here. So just review some of those guidelines before going in. I won't go through all of them right now. But just you can generally base this answer on your assessment of the damage. Know the difference between a warning and a watch. So watches are typically released first, and for a larger area, that means that the weather conditions are right. We believe tornadoes are possible. A warning means that tornadoes are imminent. We have either seen them on the ground, or we have seen things in radar that indicate they currently exist on the ground. So that's the difference. A watch, you need to prepare, but a warning, you really need to get to shelter immediately. That basically means it's almost already happening. As far as mitigation, there are a number of things that you can do. Get to a safe room, a basement or storm cellar. Go to the interior rooms. Most people remember that one. Protect your head and neck. Stay away from doors and windows. If you're outside, one thing you should not do is get under an overpass. Winds actually speed up going under an overpass, so that would be a very bad idea. The most dangerous thing is going to be the debris. So definitely try to protect yourself from debris. You could do that by getting inside of a vehicle, or even better, a very sturdy building. So after tornadoes, we did spend a little bit of time talking about flooding. So flooding, by definition, is just any time a stream overflows its channel. But we tend to focus more on the more catastrophic ones. One thing that we did as part of the flooding unit was we went back and we figured out how to calculate recurrence intervals. And we did this in a slightly different way than we had before, because every time we calculate recurrence intervals, we learn new and perhaps more complicated ways of doing it. So here's the equation for recurrence interval. In here is the number of years in the data set. So it says the recurrence interval equals n+1 divided by rank. The first thing you need to do when you look at a data set is to rank that data. So if 1 is the greatest, you would go through here and find the highest number and assign that to be a rank 1. This is the highest one that I'm seeing. And then the next highest number would be a rank 2. And the next highest number would be a rank 3. And so on until you have ranked the entire data set. And then you need to figure out what this n is. So here, 79 to 89, that's actually going to be, 11 years of data. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 years of data. So n equals 11 in this example. So the recurrence interval equals 12 divided by rank. So for the rank of 1, the recurrence interval is just 12. For the rank of 2, the recurrence interval is 12 divided by 2, which is 6. The recurrence interval of 3, that would be 12 divided by 3, which is 4. And so on and so forth. The math will get slightly more difficult as we get to things that aren't perfect divisors. But you would fill out the table by just continuing that methodology. And then you would need to plot the recurrence interval on the y-axis and the discharge on the x-axis, okay? So, and we'll keep in mind that the y-axis is logarithmic, so that means it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, blah, blah, blah. Okay, so that's how that logarithmic scale works, so watch out for that. And then you would just physically plot these. Now, this is going to be easier if you have something like a stylus like I do to draw on the screen. If you don't, you can make, if you have access to a printer, use that. If you don't have access to a printer or a stylus, you might be able to copy and paste the graph into Paint and add circles in the appropriate places in Paint. If you're just working on your phone, you're actually probably better off just trying to draw the entire graph by hand. And if you do that, just make sure that you do keep it a logarithmic plot. All right, I'm going to just put the numbers that I have on the plot here. So recurrence interval is 12 and discharge is 832. I'm going to go find what I think it might be 832. Okay, and 12. Something. Oops. Something around there. I understand it might be a little messy. All right, now for the next one, I want a discharge of 670, recurrence interval of 6, discharge 670, recurrence interval 1, 2, 3, 4, 5, 6. And I'll go ahead and do one more. For this one, the recurrence interval is 4, and this is 664. Actually, I'm really close to here. 2, 3, 4, about like that. So you are going to plot as many points as you're given. I think it's 5. And then you need to draw a straight line, just your best fit straight line, connecting those. I do recommend using a straight edge. And the next question you're likely to be asked is, what is the discharge of a 100-year flood? So you go to a 100-year recurrence interval, and see where your line crosses, and then you can just read the value of the 100-year flood. So it's between 1,100 and 1,200 cubic feet per second in this example, okay? So I know that a lot of the class was actually absent on the day that we did this. We had about 50% there, but hopefully this explains it. The things to remember are N is the number of years in the data set. Rank means give a 1 to the biggest discharge, a 2 to the next biggest, and so on. Complete this table, and then just plot the recurrence interval and the peak flood discharge. Okay, so that's the other somewhat complicated thing you have to do, but hopefully it's not really that bad. It's actually a little bit repetitive. All right, I think it was just 2 or so more slides here. So we're almost done. Other things to talk about with flooding are causes of flooding. So you could have a storm that dumps a lot of water in a small amount of time, or you could have raining for days and days and days, or you could have a dam break, or you could have snow melt. There's all sorts of causes for floods. But at a more basic level, floods are caused when water returns to streams too quickly. Okay, so if water is falling on the ground surface, if it can go into the ground and into the groundwater flow, then you're less likely to have a flood. But instead, if water falls on the ground and it's all forced into surface runoff, that's going to go straight to a stream really fast, and that's going to cause flooding. Okay, so you should be aware of both those sort of first order reasons for floods, the rainfall, as well as the fact that impervious surfaces mean less water is going into the ground, meaning more water is flowing across the surface and into those streams faster, which leads to flooding. So one way to mitigate flooding would be to have more permeable surfaces, whether that be especially engineered concrete that lets water flow through, or whether that be sort of returning an area to a more natural ground surface. So that's what's here in these wetlands next to the city. They are protecting that city from flooding just by being there. Other tips for flood mitigation can be seen over here. I'm not going to go through all of them, but in general, mitigation is going to include things that you do before, during, and after an event. And never forget things like insurance are a type of mitigation. Evacuation is always mitigation. Education and building practices and all of these sorts of things count as mitigative actions, because again, mitigation is just anything at all that you can do to lessen the impact of a hazard when it occurs. Okay, we've made it to the end. Do you have additional? I'm actually going to stop sharing this screen. Do you have additional questions? Nothing?
I've got nothing.
Okay. Well, hopefully this helped. I guess other things that you might want to know. The assessment folder should appear at noon today, and it's separated into 2 lists. One list is things that are timed, and another list is things that are not timed. Examples of things in the not timed list, your essay question, you've had it for weeks, so I'm not going to try to put a time limit on that. Also, actually the recurrence interval question that asks you to calculate the recurrence interval, that also isn't timed, and possibly a couple other things, but I haven't quite finished deciding on that. Things that are timed include the more sort of traditional exam and some of the other assessments. Some of these are available if you go into the individual units, there should be in a lot of them, well, I guess it's only one unit, but there's a folder that has example assessments. So if you study that, that can help you a lot. Things to be ready to do, and it'll say this when you go into the assessment folder. There's a lot of things that do ask you to make a sketch, and so you need to either be capable of doing that on your device or have a blank sheet of paper with you that you are ready to create that sketch on. And the time limit ones have been done so that you should have plenty of time to take a photo and then upload that to ACE. If you do have any issues, just send me an email if you sort of timed out or you needed extra time or maybe your internet access got cut off in the middle of something. Just shoot me an email, and whatever it is, I'm sure we'll figure it out. Any other questions about sort of the format or anything?
Would you be so kind and repeat when the test is? What day? Is it a Thursday?
So the assessments are opening up today at noon. You have until Friday at 5 p.m. to finish all of them.
Okay.
Hopefully it won't take more than 2 hours for most people, but it might, especially if people are going a little bit slower, just because you do have access to your notes. That's fine. You should be using your notes. I don't recommend Googling things on the internet. You can actually get into some pitfalls that way, but you're more than welcome to use your notes. And yeah, you have all week to do it. The only thing that I ask is that you don't discuss it with anyone else in the class.
Sounds good.
Any other questions? Okay, so the only other thing I was going to do was introduce my dogs, but I think I'm actually going to make a whole video, and then if you feel like meeting my dogs, you can watch the video introduction to my dogs, and I'm going to post that later today. I'll also be posting this, and I think I will go ahead and make a short sort of corrected version of that mountain problem so that people can just see it start to finish correctly. Okay, so if nobody has anything else.
I have a question.
Yes.
So for the what was it? The last one we did with the graph, the recurrence interval.
Mm-hmm.
So for the test, we're going to need to draw out a graph for that.
So you would only need to draw the graph if you don't have access to a computer. If you have access to a computer, even if it's not a touch screen, you're probably better off like using Paint or some other program to edit the graph that's given. But if you don't have that, if you are, for example, only using your cell phone, then yes, you would want to just sketch an approximate graph. You don't need to draw all those little lines in there. You would just need to draw the lines corresponding to 1, 10, 100, maybe 1,000.
So after we edit the graph, will we need to like save that as a file and submit it?
Yes.
Okay.
Now, one issue that I don't know if will happen or not is some people will be able to combine that and submit, you know, one page, but there might be other assessments where, you know, you have multiple sketches and maybe that's multiple pages. If you ever get into a situation where ACE is only letting you upload one, go ahead and upload any additional documents that you have to your, oh, I forgot what it's called, your Dropbox, because that'll have a timestamp on it and it'll let me know that you had that at the same time and it was just an ACE issue. And I'm not aware if that will be an issue. I just don't know if ACE is going to tell you you can only put in one document when you might have two.
Okay, thanks.
Mm-hmm. Anything else? Okay, then I am going to work on getting the rest of your assessments up there. They should all be up there and available by noon today, but there's no reason you need to do them by noon today. You can take your time, go through some of the old course materials. If you missed the day that we did recurrence intervals, you might want to go back and look at that assignment. I believe that the key is there as well, so you can check that you're doing it properly. I'll check on that to make sure that's true. That the key for recurrence intervals is there. So yeah, take your time preparing, and then, like I say, hopefully it'll only take you 2 hours, but if you are using your notes, it might take more like 3, just because you're being a little bit more thorough. Okay? Well, I hope everyone has a good week. This week will be online just for virtual office hours if you want to drop in from 10 to 11 again on Thursday, but also every day, and this will be true for the rest of the semester, I'm available every day from 1 to 2, and I'll be sending out an email on ACE about that later today, but you can always just drop in and see me face-to-face from 1 to 2 Monday through Thursday. All right, happy studying and stay safe, and hopefully I will catch up with all of you later.
Stay safe as well.